The first law of motion, from Aristotle to Galileo to Newton. You ask any young student about Galileo, and they may mention a story or two about discovering gravity by dropping some objects from the Leaning Tower of Pisa. Whether absolutely true or not, Galileo did not discover gravity. That'd just be weird. People floating around, just waiting for someone to discover gravity. The person who discovered gravity is probably some Neanderthal named Ug-Ug, who lived about 30,000 years ago. How about this law of motion from Newton? The first law of motion. Let's not go back as far as Ug-Ug. Let's start with Aristotle. Here are a few observations many people have made during and since Aristotle. A rolling ball will eventually come to rest. If you throw a rock over a lake, it will fall through the air and sink to the bottom. A campfire will seemingly rise in the sky. Sometimes you even see red sparks fly higher and higher. All of these motions were described by Aristotle as natural motion. One way to describe it would be to say elements seek their natural place with other elements. Earth with earth, water with water, air with air, and fire with fire. Try it. Where does water naturally go when it rains? I hope you notice it falls through the air and runs towards where other bodies of water have collected. Try another. Blow bubbles underwater. Where does the air naturally go? I hope you notice it goes up towards where other air has collected. The opposition to this natural motion, Aristotle described as violent motion or a violent action. This is taking that rock away from the earth and throwing it through the air. Aristotle's model looked something like an onion with 4 major layers. The inner layer is earth, followed by water and air. Fire was the outer layer. Let's consider a ball rolling across the ground. It eventually comes to rest. Aristotle would have said something like, since we are no longer pushing the ball, we are no longer exerting a violent action on it. The ball's natural place is to come to rest. Given this logic, let's analyze an arrow shot through the air. As an arrow flies through the air, it does not plummet straight to the ground the moment it leaves the archer's bow. Instead, it keeps going through the air. The classical explanation is that as the arrow pushes through the air, it empties a space behind it. As the air rushes in to fill this void, the air pushes the arrow forward. Thus, a violent action, arrow by the air. Galileo comes along and refines this concept with inertia. Galileo did not believe the ball came to rest because it desired to be in its natural state. The theory of inertia says that an object's inertia resists a change in motion, so the ball should roll on forever. The ball only stops rolling because an external force, friction, causes the ball to stop. The more inertia an object has, the harder it is to change its state of motion. It's popular, we see, that the first law is stated: an object at rest or an object in motion will remain at rest or in motion unless acted upon by an outside force. This is usually known as Newton's first law of motion. Obviously, Newton did not invent the law of inertia, but he presented it in one of his 3 laws. In current application, students reference constant velocity going hand in hand with an object experiencing balanced forces. Yes, an object maintaining motion, same speed, in the same direction, needs no net force acting on it to maintain this velocity. This goes for any velocity: 0, 10 meters per second, 100 miles per hour, or terminal velocity. So, put into your own words the first law of motion. Here are a few examples from students.
If you have an object, like just say you have an object and then you push it, it'll keep going until forces like say friction or something slow it down.
The object in motion stays in motion unless it's acted upon by an outside force.
An object will not accelerate or decelerate without an unbalanced force acting.
If the forces are balanced, then, or like if it's constant velocity, then the forces are balanced, and if the forces are unbalanced, then it's not constant velocity.
Okay, so an object that's moving will stay moving until something acts on it, like someone pushes it or the friction of the floor stops it.
An object in motion will stay in motion unless acted upon by an outside force.
The third law of motion, misunderstood by many. When Newton wrote Principia, his observations and data were not new. The three laws of motion were well-stated conclusions of hundreds of years of data and descriptions. In the first episode, you heard about the first law. In this episode, we'll explore the third law. We skip over the second law in order to compare and contrast the first and third. The first law is often confused with the third law. Many students have memorized the third law, and the tempo at which they speak sounds something like this. For every action, there is an equal and opposite reaction. Or, for every force, there is an equal and opposite force. While this wording is not wrong, the application by instructors, either through personal ignorance or pedagogical ignorance, leads students to an understanding that a book at rest on a table explains the third law, with a gravitational down being equal and opposite to the supporting force up. Yes, these forces are equal and opposite, but this explanation resides with the first law. The book remains at rest due to the two forces balancing each other. This confusion breaks down when one drops the book. Try it. As the book drops to the floor, what force is acting on the book? Most students of physics easily reply, gravitational. Yes, there is a gravitational force on the book exerted by the Earth down. Okay, so for every force, there's an equal and opposite force. Let's focus on every. Since Newton was specific on every force having an equal and opposite, then what is this strain reaction force to the action of gravitational on book by Earth down? At the snapshot of the book falling, that is, after it left your hand, and before it slams into the floor, is there any other object interacting with the book? Some would likely state there exists some air resistance. If air resistance was equal and opposite, then the book would revert to having balanced forces and fall at constant velocity. This supports the first law. A little silly since we know the book is speeding up as it falls. The third law should allow students to think outside the box, or in this case, outside the book. Let's go back to the book sitting motionless on a table. The table is supporting the book with a push upwards. Physics types refer to this as a normal force. Normal in this case referring to perpendicular force between the two objects. So, there is a normal force on the book by the table upwards. If this is action, then the reaction is the normal force on the table by the book downwards. After all, you cannot touch without being touched. Let's revisit the following book. The action is gravitational on book by Earth directed down. Therefore, the reaction is gravitational on Earth by book up. Yes, these are third law pairs. Which one do you suppose is the larger force? Gravitation on book by Earth or gravitation on Earth by book? The answer, they're equal. Here are a few student explanations of the third law.
If you push on something in one direction, they're going to push back with an equal amount of force in the opposite direction.
Force has like a force that's acting on it like in the opposite direction, but they're equal.
For everything the forces you exert, a force will be exerted back on you, an opposite force. So like when you're standing on the floor the floor is acting on you with an opposite force going in the opposite direction with the equal force because you're staying.
Every action is has an equal and opposite reaction.
With a car that's at rest, when that's the snapshot of when they collide, they exert equal and opposite forces on each other.
Whenever an object, emits a force upon another object, that object returns an equal and opposite force on the object.